We're going to open up the lifter typedef. We can paste it right in. So now we've got the device references we need for the hardware, but we haven't added the information for the state data. So let's do that now. First, let's add an enum. You get that from the ring and enum palette. Choose enum and place it down. An enum, if you haven't seen one before, is essentially a fancy numeric control. Although the data type is numeric, it allows you to enumerate each of those numbers. In other words, it allows you to give them a name. We're going to use this enum. We're going to call it the lifter state. This is the way that we're going to keep track of what state our machine is in. The way that we attribute those names to the various states of the enum is by right-clicking and choosing Edit Items. This brings up a window that allows us to attribute the names to each of those numeric values. So let's refer back to our state diagram and create all of the states for our enum. So the first is start. The next is moving down. And a shortcut is to push the tab key to get to the next row. Then wait for ball. Delay before raising. Moving up. And that's it, because the next state after moving up is actually to go back to moving down. So we've completed our state enum. And an interesting point here is actually to take that enum and turn it into a typedef itself. The reason for that is you're going to find it makes life a lot easier later on when it comes time to actually program the state machine. So it's just a rule of thumb. Whenever you create an enum, go ahead and create a typedef of it. So let's do that. Customize control. Change the type to typedef. Save it. We'll call it the lifter state enum. Just close it, allow it to replace, and we can throw that inside our lifter typedef. So now we've got all the device references, we've got our internal state. Now let's add just a few more parameters. Well, we had that numeric control, which was delay end time. We'll call it delay end time in milliseconds. We'll change its representation to U32, just because we know that the tick counter, which is tracking the millisecond elapsed time, is actually a U32 data type. So we'll put that in our shifter. And now let's add a few more pieces of information that are just there for convenience. They don't technically have to be stored, but we're going to see as we get a little further on into this process that there's a lot of value to keeping track of all of the values that you read. So let's create a numeric control for the current motor speed. Put that in, and let's add 3 Boolean values, one for each of the digital inputs. So we have the lower limit switch value, we have the upper limit switch value, and we have the ball sensor value. We'll put those three guys inside the typedef, and if we just review, we've got the device references for all of our hardware that we're talking to. We've got the upper limit switch, lower limit switch, and ball sensor. We've got the device reference for the motor that we're trying to drive. And we've got all of our internal parameters. We've got our state, which contains all the different states of the system. Start, moving down, wait for ball, delay before raising, and moving up. We've got our delay end time, our current motor speed, and the state of our 3 digital inputs. So now that we can save and close that typedef, we can save and close robot data, and now we have a receptacle into which to put all of these device references. So if we pull this down, naturally we see our lifter typedef, and we see room to place all these device references which we've opened. So we've got the upper limit switch, lower limit switch, and ball sensor, and motor. Let's move some things around to make a little bit more room. Let's connect up our device references. And the other thing we could consider doing at this point is also to set the lifter state. Remember that when we start the program based on this state diagram, we want to make sure we begin in the start state. So it's always important to initialize that. If we right-click on that input, we can choose Create Constant, which allows us to specify the start. So now that we've initialized everything, we can now proceed and actually write the code that we need to actually do and execute this state diagram. So let's save our begin VI, close it, and take a look at our robot main. The code we're going to write is going to go inside the teleop VI. Let's open that up. And as we've seen before, whenever we add something into the robot data, we know that we get access to that typedef everywhere automatically. So what we're going to do is we're actually going to make a sub-VI which takes this lifter typedef as an input and brings it back out as an output. So remember the shortcut to creating a sub-VI like that. We just create a temporary sequence. We wire the inputs that we want. We use a bundle by name to have a place to wire it out again. And then we make a sub-VI from this. So we select the sequence that we've just created, choose Edit menu, Create sub-VI, and there we now have a sub-VI which takes that typedef as an input and outputs it again for later being inserted into the main robot data typedef. So we have this new sub-VI now, which we can save and call our lifter state machine sub-VI. We can make a very quick icon. Rename our automatically named inputs to have the right names, lifter typedef in and lifter typedef out. So now we've done everything we need to do except write the code. So now the hard work begins. At the heart of the functionality of a state machine is the ability to perform different actions depending on what state we're in. If we use an unbundle by name to extract our state, we can go ahead and delete this sequence now. If we use this unbundle by name to extract the state, we need to perform something different on this code depending on the value there. Naturally, that means we need a case structure. So we have a case structure which, when we wire it to the lifter state, provides us with the ability to define different code for every single case. So let's begin with the start case. Just going to shrink down and hide some of these other sub-VIs so that we can always see the state diagram that we're trying to build to. We'll keep this on the screen here. So what happens in the start state? Well, really two things happen. One, a motor speed is set, and two, it transitions to a new state. So how are we going to set the motor speed? Well, we've seen how, and we've done this many times. We know how to talk to any of these devices. We basically just need our device reference, and then we need the right WPI library call. Robot drive, advanced, motor control, set speed. So the first thing we're doing here is we're setting that motor speed according to our state diagram to be minus 0.5. And then the second action we're doing is we're actually changing the state. And that's the real power of a state machine, the fact that a state can decide where the software should go next. So in order to change this state, which is stored in this cluster, we need a bundle by name. So we choose the bundle by name. We wire up, remember, the middle terminal is connected to the input value. Just make a little bit more room here.